Welcome everyone to Innovation Instigators, the podcast where we bridge the gap between cutting-edge technology and business strategy. Today, we're diving into something truly fascinating, the idea that large language models, or LLMs, the text wizards we know, can now effectively see and hear, without specific multimodal training.
It sounds almost like science fiction, doesn't it? But the research we're discussing today, specifically around a technique called MILS, makes a compelling case.
And from a business perspective, anything that promises powerful new capabilities without the often hefty price tag and time sink of task-specific training, well, that gets my attention immediately. It speaks to agility, a core need in today's market.
Absolutely. So let's unpack MILS, the Multimodal Iterative LLM Solver. Expert 1, can you give us the high-level concept? How does this magic trick work?
Happy to try. At its heart, MILS is surprisingly elegant. Think of it as a two-part system. You have a standard, off-the-shelf LLM acting as a generator. Its job is to propose candidate solutions like image captions or prompts for image generation.
And then comes the second part, the scorer. This is typically a pre-trained multimodal model, like CLIP or SIGLIP, which understands relationships between different data types, like images and text, or audio and text.
Okay, so the LLM generates ideas, and the multimodal model scores them. How does that lead to a final answer?
It's iterative. The LLM generates a batch of candidates. The scorer evaluates how well each candidate matches the input, say, how well a generated caption describes an image. It ranks them.
Exactly, and those scores, along with the top-scoring candidates, are fed back to the LLM as text feedback for the next round. The LLM then uses this feedback to generate better candidates.
So it's a feedback loop. The LLM essentially learns on the fly, at test time, guided by the scorer. It's like a writer drafting headlines and an editor giving real-time feedback on which ones resonate most with a target image or concept.
Precisely. It's a clever way to leverage the LLM's reasoning and text generation prowess for tasks it wasn't explicitly trained for. It's test time optimization, kind of like tuning an instrument right before the performance, rather than building a whole new one.
And the results are quite stunning. The paper shows state-of-the-art performance on emergent zero-shot captioning for images, videos, and audio. That's huge, one framework tackling multiple modalities.
Emergent Zero-Shot, can we clarify that for our business leaders? Does this mean plug-and-play multimodal AI?
Sort of. Zero-shot here means the model wasn't trained specifically for, say, image captioning using curated caption data. It uses pre-trained components, the LLM trained on text, the scorer trained on paired multimodal data like images and web text, but MILS itself requires no new training for the task of captioning. It figures it out during inference.
Right? Think of the scorer like CLIP. It learned alignments between images and text from vast web data, but not necessarily clean, descriptive captions. MILS uses that learned alignment signal to guide the LLM, which is good at generating descriptive text, towards producing a good caption. It's combining strengths.
Let's dig into those applications. Expert 4, image captioning, how does it compare?
The paper shows MILS outperforming or being competitive with specialized zero-shot captioning methods, like MECAP. And qualitatively, the captions often seem more accurate and natural. For instance, generating Boston Terrier's sharp teeth firmly gripping a rope toy tightly instead of something more generic or slightly off.
And it extends surprisingly well. For video captioning, using the same LLM generator but swapping in a video text scorer like ViClip, it competes well even against models trained on video caption datasets. Same story for audio captioning, using ImageBind as the scorer.
This flexibility is key, using the same core approach but swapping modules for different tasks and modalities. That implies faster development cycles, less need for specialized expertise for every single new multimodal task. That's a significant potential cost saving and speed advantage.
So it's not just understanding media, but generating it too. The paper mentions improving text-to-image generation.
Yes, this is where it gets really interesting. The LLM isn't just generating a final output, it's generating better prompts for a text-to-image model like Stable Diffusion or, as tested, LDM and FLUX.1.
The LLM acts as a prompt rewriter or enhancer. It takes an initial user prompt, say a cat sitting on a fence, and iteratively refines it based on feedback from a scorer that judges image quality and prompt faithfulness.
For scoring generated images, they use something like PicScore, which predicts human preference for image quality based on a prompt. So the feedback loop optimizes for aesthetically pleasing and accurate images.
It's like having an AI creative director, whispering better instructions to the AI artist.
Exactly. And the human evaluation results in the paper bear this out. Users consistently preferred the images generated using MILS-enhanced prompts for both quality and faithfulness compared to the base text-to-image models.
Think about the implications for creative industries or marketing content generation. Instead of laborious manual prompt engineering, which, let's be honest, is often more art than science, MILS could automate finding those magic words that unlock the best output from a generative model.
That resonates. Reducing the friction in using these powerful generative tools is a major value proposition. If it makes generating high-quality, on-brief assets easier and faster, that directly impacts campaign workflows and content pipelines. It's applying the 80-20 rule. MILS handles the heavy lifting of prompt optimization.
And it goes further, style transfer. By using a scorer that measures style similarity, like Graham matrix distance, famously used in neural style transfer, and content similarity, MILS can figure out the text prompt needed to instruct an image editing model to apply a specific style to a content image.
Wait, the LLM figures out the text to describe the style edit, without actually seeing the style image's features directly.
Correct, it's working purely in the text domain, guided by the scorer's feedback on the output images produced by the editing model using the LLM's suggested edit prompts. It's optimizing the instruction, not manipulating pixels itself.
This gradient-free nature is a key advantage of MILS. Many previous approaches trying similar things relied on backpropagating gradients through models, which can be complex and restrictive. MILS just needs scores.
Okay, mine's slightly blown here. And then there's cross-modal arithmetic, adding concepts from images and sounds. Expert 4, walk us through that.
This is where MILS's ability to invert multimodal embeddings back into text really shines. Prior work could map embeddings to images, but MILS maps them to discrete text.
So you take an image, use MILS with an image text scorer to generate a text caption. You take an audio clip, use MILS with an audio text scorer to generate another text caption.
Then you feed both text captions to an LLM and ask it to combine the concepts into a single, coherent scene description.
Like image, a red car parked, plus audio, birds chirping, becomes a red car parked near trees with birds chirping.
Exactly, or something more imaginative. Then you take that combined text description and feed it into the MILS-enhanced text-to-image generation process we just discussed.
So you effectively add the semantic concepts from the image and the audio clip to create a new image representing both. Figure 7 in the paper has great examples, like combining birds chirping audio with a people talking image to generate an image reflecting both concepts.
Okay, that's genuinely cool. I'm tempted to try it with a picture of my overflowing inbox and the sound of a deadline whooshing by. Maybe not. Expert 5, this sounds amazing, but what are the practical hurdles? Is this computationally expensive? Slow?
Ah, yes, the million-dollar question. It is an optimization process run at inference time. It requires multiple calls to both the LLM, generator, and the multimodal model scorer. The paper mentions running for 10, sometimes up to 20 steps for convergence.
So it's definitely more compute intensive than a single forward pass through a standard model. Real-time application might be challenging currently, depending on the complexity and the models used.
Performance also seems quite dependent on that initial candidate set for tasks like captioning. A good, diverse starting pool is crucial to avoid getting stuck in local minima and to give the generator good initial ideas to work with. Generating that initial set itself takes some thought.
But let's weigh that compute cost. Expert 5 raises valid points about inference time and setup. However, compare that to the cost in terms of data curation, specialized expertise, and weeks or months of training time required to build a bespoke multimodal model for each new task. MILS offers a trade-off, potentially higher inference cost for vastly lower development cost and much greater flexibility.
That's a great point, Expert 3. Building on that, the training-free aspect democratizes access. Smaller teams or companies without massive GPU clusters or specialized data labeling pipelines could potentially leverage state-of-the-art multimodal capabilities using off-the-shelf components combined via MILS.
I find this fascinating. While everyone is focused on the tasks MILS enables, captioning, generation, arithmetic, maybe the real paradigm shift here isn't the what but the how. It suggests a future where LLMs act as general-purpose reasoning engines coordinating specialized sense modules, the scorers. But I wonder, are we potentially just shifting the bottleneck? Is the quality and nuance of the scorer model now the absolute limiting factor?
That's a sharp insight, Expert 6. The scorer is indeed critical. Its ability to provide meaningful, granular feedback dictates the upper bound on MILS's performance. Garbage in, garbage out applies to the scores too. If the scorer thinks a bad caption is good, the LLM might reinforce errors. We saw in the ablations that better scorer models, like SIGLIP versus older CLIP versions, did lead to better results.
And the choice of scorer isn't always obvious. For style transfer, using gram matrix distance is clever, but it has known limitations in capturing all aspects of artistic style. So, the effectiveness for complex, nuanced tasks is tied directly to how well we can mathematically score the desired outcome.
So the Achilles heel, if there is one, might be the sophistication of our current multimodal scoring models.
Potentially, or perhaps it's an opportunity driving research not just into bigger LLMs, but into much more perceptive and fine-grained scorer models that can provide the high-fidelity feedback needed for truly complex multimodal reasoning and generation. As Peter Drucker supposedly said, what gets measured gets managed, or in this case, optimized.
From a strategic standpoint, though, even with current limitations, the ability to rapidly prototype and deploy multimodal applications using existing assets is powerful. It allows for experimentation and finding product-market fit much faster than traditional approaches. We can test hypotheses quickly.
It feels like we're seeing LLMs evolve from pure text processors into orchestrators, using other models as their eyes and ears. It's less about teaching the LLM to see, and more about giving it a tool that sees and the ability to iteratively ask, "Am I describing this correctly?"
That's a perfect analogy, host. And as LLMs get better at reasoning and following complex instructions, and as their context windows grow allowing for more feedback history, MILS-like approaches should become even more powerful and efficient.
Efficiency is key for broader adoption. Reducing the number of optimization steps needed, maybe through better initial prompts or more informative feedback structures, will be crucial.
I'm excited about extending this to other domains. Could MILS work for 3D scene understanding or generation, using scores that evaluate geometric consistency or physical plausibility? Or generating text descriptions for complex sensor data in industrial settings?
The long-term potential is staggering. If this iterative test time optimization proves truly generalizable, LLMs could become the central brain, coordinating a vast array of specialized sensory and generative modules, tackling problems far beyond what any single monolithic model could. It hints at a more modular, flexible future for AI.
This has been an incredibly rich discussion. We've gone from a seemingly simple concept, LLM plus scorer plus feedback loop, to exploring state-of-the-art results in captioning, groundbreaking approaches in generation and editing, and even mind-bending cross-modal arithmetic.
Key takeaway for business leaders: MILS represents a potential shortcut to sophisticated multimodal AI capabilities, offering flexibility and speed-to-market advantages by leveraging existing models in novel ways. Keep an eye on the trade-offs, especially inference cost, but the strategic potential is undeniable.
For the tech leaders, this highlights the power of emergent capabilities and clever system design. It's not always about building bigger models, but about finding innovative ways to combine existing ones. The interface between the generator and scorer and the optimization process itself are fertile ground for future research.
Fantastic points. Thank you all, Expert 1, Expert 2, Expert 3, Expert 4, Expert 5, and Expert 6, for sharing your deep insights today. It seems LLMs might not need eyes and ears if they can effectively borrow them and learn how to use them on the fly. That wraps up this episode of Innovation Instigators. Join us next time as we tackle another frontier where technology meets strategy. This paper introduces the Multimodal Iterative Large Language Model Solver, or MILS. MILS gives large language models capabilities to understand multiple types of data. This includes images, video, and audio. Remarkably, it achieves this without any specific training for these tasks. The approach uses the language model existing reasoning abilities. It works through an iterative process at the time of use. MILS uses two main parts, a generator and a scorer. The generator, usually a large language model, creates potential outputs like captions. The scorer, an existing multimodal model, evaluates how good these outputs are. Multimodal models understand relationships between different data types like text and images. The scores guide the generator to create better outputs in the next step. This optimization continues until a good solution is found. This method requires no task-specific data collection or model training. MILS set new state-of-the-art results for zero-shot captioning. Zero-shot means performing tasks the model was not explicitly trained on. This includes captioning images, videos, and audio effectively. The approach also improves text-to-image generation quality. It uses the language model to rewrite and enhance image creation prompts. MILS can perform image editing tasks like style transfer. It enables novel applications like cross-modal arithmetic. This involves converting different media types to text, combining them, and generating new media. A key finding is that language models can handle multimodal tasks through guided iteration. The authors note some limitations. Performance depends on the quality of the generator and scorer components. The iterative process can also be computationally intensive and slow. Future work could improve speed and apply the method to more areas like 3D tasks. Improvements in language models and multimodal models will likely enhance this approach.